You paste a 50-page report into your AI model. The model says it read everything. You ask a question about a detail buried in the middle. The answer is wrong, or worse, confidently invented. This is not a random glitch. It is a predictable failure tied to something called the context window, and the way vendors talk about it is quietly misleading you every single day. A context window is the total number of tokens a model can see at once during a single conversation. Tokens are chunks of text, roughly 3/4 of a word on average. So a 100,000 token context window holds something like 75,000 words. That sounds enormous. And vendors use these numbers as selling points, as proof that their model can handle any task you throw at it. Here is the problem. The advertised token limit describes the maximum size of input the model will accept without throwing an error. It does not describe the size of input the model will process with consistent, reliable accuracy. Those are two very different things, and the gap between them is where your important information goes to disappear. To understand why, you need a rough mental model of how these systems work. Large language models use a mechanism called attention. During processing, every token in the context pays attention to every other token to figure out which ones are relevant to the current task. The model learns these attention patterns during training. And training, it turns out, creates strong biases about which positions in a sequence matter most. Multiple research teams, including a widely cited group from Stanford, ran a simple but devastating experiment. They gave models a long document containing a specific answer to a question. Then they moved the position of that answer around. At the beginning of the document, models recalled it well. At the end, recall was also solid. But when the answer sat in the middle of the document, accuracy dropped sharply. The models were not lying on purpose. They were architecturally less likely to surface information from that middle zone. This pattern now has a name in the research literature, the lost-in-the-middle problem. It has been confirmed across multiple frontier models. It is not a bug that will be patched in the next update. It reflects something deep about how attention-based architectures assign weight to positions in a sequence. The middle is the weak zone, and the longer your context, the larger and weaker that middle zone becomes. Now layer a second problem on top of that. As a context grows longer, the model has to spread its attention across more and more tokens. Think of attention as a budget. In a short conversation, that budget is concentrated. Every piece of information gets a meaningful share. In a 60,000 token context, that budget is spread thin. A single important sentence is competing with tens of thousands of other sentences for a fraction of the model's processing focus. Researchers call this attention dilution. The effect compounds with length. At 10,000 tokens, dilution is modest. At 50,000 tokens, a critical instruction or fact can become nearly invisible to the model, even though it is technically inside the context window. The model did not forget it in the way a human forgets. The model processed it, but with so little weight that it had almost no influence on the output. There is also a third factor that most people never think about, the quality of positional encoding at extreme lengths. Models are trained on sequences up to a certain length. When you push past the lengths common in training data, the model's ability to track where it is in the sequence can degrade. Some models handle this better than others through techniques like rotary position embeddings or sliding window attention. But no current model handles it perfectly, and very few are transparent about where their reliable range actually ends. So what does this mean in practice? Let us say a model advertises a 200,000 token context. Based on published research, reliable factual recall often starts degrading somewhere between 20 and 50% of the advertised maximum, depending on the model and the type of task. For a 200,000 token model, that could mean performance starts slipping at 40,000 to 100,000 tokens. You are using only half the window before the cracks appear, and the vendor's spec sheet tells you nothing about this. The situation is different for different kinds of tasks. Summarization degrades later than precise retrieval. Creative tasks are more forgiving than tasks requiring exact quotes or specific numbers. Code completion in a large codebase context is particularly vulnerable because even a single wrong variable name or missed dependency can break everything. Knowing your task type tells you how cautious to be. Let us talk about what you can do. The first and most powerful strategy is to restructure your inputs so the most important information appears at the beginning and at the end of your prompt. Put your core instructions and the most critical facts at the top. Put a summary or restatement of the key constraints at the bottom. Leave the supporting or background material in the middle where possible, not the details the model needs to get right. The second strategy is chunking. Instead of feeding the model one enormous document, break it into meaningful sections and process each section in a focused call. Then aggregate the outputs. This keeps each individual context shorter, more concentrated, and inside the zone where attention is reliable. Many production AI systems already do this automatically, but if you are working directly with an API or a chat interface, you need to do it manually. The third strategy is prompt compression. Before feeding a long document to a model, use a smaller, faster model or a dedicated compression tool to strip out redundant sentences, repeated facts, and filler language. Research from groups like LLM Lingua at Microsoft shows that compressing prompts by 50% or more often causes less accuracy loss than you would expect, because much of the original text was low information content to begin with. The fourth strategy is retrieval augmented generation, or RAG. Instead of putting an entire knowledge base into the context, you store it externally and retrieve only the most relevant chunks at query time. This keeps your actual context short and targeted. RAG is not perfect, and retrieval quality matters enormously, but for large document sets it dramatically outperforms naive full-context approaches for precise retrieval tasks. A fifth, simpler strategy that is often overlooked: test your model on your actual use case before you trust it with anything important. Build a simple evaluation. Put the key information you need the model to recall at different positions in a test context. Check the accuracy. You will learn more from 20 minutes of structured testing than from reading any spec sheet, including this one. It is worth saying that the major labs are aware of these problems and are actively working on them. Techniques like memory-efficient attention, sparse attention, and new training methods for longer sequences are real areas of progress. Some models have improved meaningfully at long context tasks over the past 2 years. But the progress is incremental. The benchmarks used to measure it are often easier than real-world tasks, and the fundamental tension between context length and attention quality has not been solved. There is also a business dimension to this worth naming. Longer context windows are a marketing differentiator. A model with a 1 million token context window sounds more capable than one with 100,000 tokens. Vendors have incentives to advertise the maximum and downplay the reliability curve. That is not necessarily bad faith, but it means the burden of understanding the real limits falls on you, the person building with or using these tools. The practical upshot is this: treat the advertised context window as a hard ceiling, not a comfortable operating range. For anything where accuracy matters, use the smallest context that contains the information you need. Structure that context so critical details are at the edges. Compress aggressively. Retrieve rather than paste when you can. And always verify outputs when precision is required. Context windows will keep growing. The reliability curves will keep improving. But the gap between what vendors advertise and what models reliably deliver will likely persist for years, because pushing the frontier always runs ahead of solving it cleanly. Understanding that gap is not pessimism about AI. It is just accurate thinking, and accurate thinking is what separates people who get consistent results from people who blame the tool. If this video changed how you think about context windows, hit the like button. It genuinely helps this channel reach more people who are trying to understand AI beyond the marketing. Subscribe if you want more videos that go this deep. Next, we are covering retrieval augmented generation in detail, how it works, where it fails, and how to build a RAG pipeline that actually holds up under real conditions. That one is coming very soon.